Drop a solid zinc rod into a solution of copper sulfate, and an atomic swap happens almost instantly. Zinc atoms detach, give up their electrons directly to the copper ions, and release a burst of infrared heat. This spontaneous reaction is driven by a highly negative standard Gibbs free energy change. The system naturally wants to drop to a lower energy state, and it accomplishes this by shedding its excess chemical potential energy. But when this happens in a single beaker, that potential energy is completely wasted. Because the electrons transferred directly from the zinc to the copper in the exact same physical space, the energy dissipates into the surrounding liquid as useless ambient heat. To capture that energy, we have to intervene by physically isolating the reactants. We separate the zinc losing electrons, the oxidation half reaction, from the copper gaining electrons, the reduction half reaction, into two distinct environments. By separating the metals, the electrons can no longer jump directly across an atomic gap. We force them to travel over a macroscopic distance to reach their destination. That required transit is what converts the chemical potential energy into harnessable electrical work. This isolated configuration is known as the Daniell cell. In one beaker, we place a solid zinc rod into a solution of zinc sulfate. In the adjacent beaker, a solid copper rod sits in a solution of copper sulfate. We then bridge the gap between these two isolated metals with an external conductive wire, placing a voltmeter in the middle to measure the pressure of the electrons moving through the circuit. The zinc compartment acts as the anode. Here, zinc atoms undergo oxidation, shedding their electrons and leaving behind a negative charge. This establishes the anode as the negative terminal of the system. On the opposite side is the cathode. The copper ions in the solution eagerly accept those incoming electrons to undergo reduction, establishing the cathode as the positive terminal. The electrons now have a clear path. They flow from the oxidized zinc, travel up and across the external wire, and finally arrive at the copper cathode. This specific physical layout bottlenecks the reaction. It scales an atomic electron transfer up into a macroscopic, continuous electrical current. But watching the wire only tells half the story. The real bottleneck happens down inside the isolated fluid beakers. As the zinc rod oxidizes and sends its electrons away, it dumps positively charged zinc ions into the surrounding solution. The left beaker rapidly accumulates a massive excess of positive charge. Meanwhile, the right beaker is pulling positive copper ions out of the solution to plate onto the rod. This leaves behind a severe excess of negatively charged sulfate ions. This growing imbalance creates an opposing electrostatic field known as a liquid junction potential. The positive charge at the anode begins to pull the electrons back, while the negative charge at the cathode actively repels them. Very quickly, this repulsive electrostatic force grows strong enough that it instantly overpowers the original thermodynamic push of the chemical reaction. Within nanoseconds, the macroscopic current dies. The voltmeter reading drops to absolute zero, even though both beakers remain full of unreacted chemical fuel. A thermodynamically spontaneous reaction will choke itself off and halt entirely if local electrostatic neutrality is not strictly maintained. To solve this electrostatic crisis, we have to complete the internal circuit by introducing a salt bridge. This is typically an inverted U-shaped glass tube filled with an inert electrolyte, like potassium chloride, suspended in a thick agar gel. The salt bridge provides an escape valve for the charge buildup. Chloride anions migrate out of the bridge and drop into the zinc anode compartment to neutralize the excess positive charge. Simultaneously, positively charged potassium cations march into the copper cathode compartment to neutralize the excess negative charge left behind by the vanishing copper ions. By neutralizing the solutions, the salt bridge eliminates the liquid junction potential. With the electrostatic roadblock removed, the electrons in the external wire immediately resume their rapid movement. But the choice of salt inside the bridge requires precision. Why is potassium chloride the ideal inert salt for this specific engineering task? The answer lies in ion mobility. Ion mobility is a metric defining the speed at which an ion moves through a medium under an electric field. Potassium and chloride ions are selected because they travel through the gel at nearly identical speeds. If they moved at different rates, a new charge imbalance would simply form inside the bridge itself. Perfectly matched ion mobility provides a seamless internal circuit. It prevents secondary junction potentials from forming and sustains the cell's continuous electrical output. On paper, chemists use standard IUPAC shorthand notation to perfectly describe this physical layout, reading from the anode on the left, across the salt bridge, to the cathode on the right. Under standard conditions, meaning a baseline temperature of 298 Kelvin and exact 1 molar concentrations for all solutions, this specific zinc-copper configuration produces a standard cell potential of exactly 1.1 volts. But as the reaction proceeds, those concentrations change. The physical chemist Walther Nernst proved that cell potential is not a static number, but a dynamic value tied directly to the shifting chemical concentrations inside the beakers. This equation illustrates the relationship. The Nernst equation maps these concentration variables, the zinc and copper ions, directly to the physical reality of the cell's electrical output. If we isolate the reactant concentration, the copper ions in the denominator, we see how the math dictates the physics. Flooding the cathode with excess copper ions increases the thermodynamic driving force, climbing the overall cell voltage higher than 1.1 volts. Conversely, isolating the product concentration, the zinc ions in the numerator, reveals the inverse effect. Accumulating excess zinc ions at the anode actively resists the forward reaction, dropping the cell voltage below the standard 1.1 volts. A battery's real-time voltage is simply a direct mathematical readout of the shifting thermodynamic ratio between its products and reactants. Because this thermodynamic relationship is precise, it is also strictly reversible. We can test this by hooking the Danel cell up to an external opposing power source. In the first scenario, we apply an external voltage weaker than the cell's natural 1.1 volt potential. The internal chemical electromotive force is stronger than the outside pressure. The cell simply ignores the external push and continues to discharge normally, acting as a galvanic cell. In the second scenario, the external voltage exactly matches the standard cell potential. The forces are in perfect equilibrium. The electrons sit perfectly still, and no current flows in either direction. Finally, the applied external voltage is cranked up to exceed the cell's natural potential. This immense pressure overpowers the chemical thermodynamics entirely, forcing the electrons to travel backward through the wire from copper to zinc. The chemical roles reverse. The usually passive copper is forced to undergo oxidation and dissolve, while the zinc is forced to undergo reduction and plate back onto its electrode. The system has now transitioned into an electrolytic cell. An electrolytic cell is an electrochemical system that actively consumes external electrical work to drive a chemical reaction backward against its spontaneous direction. Looking at the fully functioning closed-loop macroscopic system of the battery, we see the complete architecture: the wire conducting the charge, the bridge balancing the field, and the thermodynamics driving the motion. Generating and storing electricity requires coordinating a continuous flow of electrons through an external wire, while neutralizing the resulting ions through an internal fluid. The mastery of these thermodynamic gradients is what makes modern power possible.